Right. Good morning, everyone. And of course, yesterday we had a look at a case where we had a choice of mechanism. So there was a choice of an acyl cleavage or an alkyl cleavage. And of course, for the acyl cleavage, the rate determining step was movement of electrons away from the aromatic system, away from the probe. And so we ended up with a graph of negative slope. And it doesn't matter if a group is ethyl or methyl, this movement of electrons away from the probe can happen. So for both esters, both methyl and ethyl esters um, of these substituted benzoates, you get a negative slope for that hydrolysis. However, of course, there is another mechanism available to that. And of course, that mechanism involves movement of electrons towards the probe. However, that pathway is only available to the ethyl ester because you get a primary carbocation. For the methyl case, you get a methyl cation, which is really tough to get. And so it's not really available to the methyl ester. And so the ethyl ester has a choice of mechanisms. And of course, when you have a choice of mechanisms, the faster mechanism will prevail. So you can see over here, you have mechanism A, and as you move from right to left, as you get from your electron withdrawing groups and you become electron donating, you can see that the reaction becomes slower and slower and slower. And eventually it becomes too slow that mechanism B takes over. And so you only see the product of B. So there's an interplay. Both pathways are available, but of course you only see the product from the pathway that's really fast. And on the left-hand side, it's B that's really fast, and so you only see those products. On the right, you see A. A is really fast, and you only see those products. So when there's a choice of mechanism, the faster mechanism prevails. Please, when you draw graphs, I strongly advise you to always write on the graph these EDG and EWG. I always put it there myself. You'll see on every single graph I've got electron withdrawing groups, electron donating groups, just to remind myself that the electron withdrawing groups, like the nitric groups, are on this side. The electron donating groups, like the methyl and methoxy groups, are on this side. Okay. Right. But what I want to have a look at today and concentrate on is a slightly different mechanism where the graph you get is concave down. Now, I just want to point out a couple of things. Firstly of all, this is not a curve. It is two straight lines. And so if you were going to plot in Excel like I've done, I actually plotted those three separately to get a straight line with rho of 2.67. And I plotted these ones separately to get rho, the gradient, as minus 2.51. Okay. So this is quite an interesting case. And this really, we're looking at the cyclodehydration of some phenyl triaryl methanol. So these are the systems we're looking at. And it's quite interesting that we don't just have one probe, we've got two aromatic systems that are of interest. And so we do the reaction, changing the substituents at X, Y, and Z. Okay, and because we've got more than one aromatic system, what we do for this graph is we sum the reaction constants together. So you can see over here, the sigma, capital sigma, small sigma, it seems quite strange, but simply it's a sum of the substituent parameters. So if you've got a para-nitro and a para-nitro, you would add both of those together. But of course, we're using sigma pluses here. And if you're using sigma pluses, just be aware that that is through conjugation electron donating. So we need to explore that, why we use sigma pluses and the sum of sigmas on this side as well. So really, we need to try and explore this mechanism. How are we getting from this substituted methanol to the cyclic system that we have there, and why, when we look at the rates, and we plot the rates, we get this distinct difference on both sides of a Hammett plot. Okay, so let's have a look without ado at the mechanism. The mechanism is relatively straightforward. Okay, so what we start off with is the substituted methanol there, and of course you protonate it, and when you protonate it you end up with a really nice leaving group. That's just water as a leaving group. Okay, and that's going to be fast. Protonation is going to be really fast. Right, so the next step, what happens is we have movement electrons away from the probe as you lose that leaving group, and you end up with a carbocation, right? And then of course we get attack by the double bond of that carbocation center, which breaks the aromaticity, and then of course we reform the aromatic system and lose a proton in the process, and we end up with the product that we see over there. Okay, so the question is, what's happening on the left-hand side here? What's happening in this side of the graph where the gradient is 2.67? We know that if the Hammett plot shows a positive gradient with such a large value as 2.67, that the rate determining step, okay, there's a question of what's the probe. A probe is a word that I use. On the aromatic system, if you're trying to explore a reaction, what you do is you change your substituents. And so the aromatic system here, we're going to change, you see the substituents here. We're going to try have an unsubstituted system here. We're going to try and put electron withdrawing groups here. We're going to try and put electron donating groups here. So we're trying to probe what's going on at the reaction center. So this here is our center that we're using to explore the reaction. So if you're looking at a Hammett plot, remember that over here, if electrons are moving away from the aromatic system, if they're moving away from this probe here, then electron donating groups are going to aid that. And electron withdrawing groups will stop that. So this here, that's what I mean by the probe. Does that answer that question? Yeah. So please, when you're trying to determine electron movement, you need to look where you're substituting. Okay, so it's very important because you can see over here, if you're sitting over here, electrons are moving away from you. That's not what we're interested in. We're interested in our probes here. Are electrons coming towards us or coming away from us? If we're sitting here, are electrons coming towards us, away from us? And can you see that if we're sitting here, electrons are moving away from us? And if we're sitting here, electrons are moving towards us. So this is what we're using to probe the reaction. So those are probes into the reaction, what I call a probe into the reaction. Okay. Right, so on the left-hand side, we know that if we've got a positive slope, we've got electrons moving towards the probe in the rate determining step. So this must be the step we're looking at. Can you see? Because if over here we've got electrons moving towards us, which means that, of course, how can we aid that? Well, if we have got strong electron withdrawing groups, we'll speed this up. And if we've got strong electron donating groups, we'll slow it down. You can see what's happened. Electron donating is over here. It's really slow. And as you become more and more electron withdrawing, it's faster and faster. So that's what's happening. This is the step we're seeing over here. That is the step we're seeing that is rate limiting. Okay, so let's see. I hope you can see that if you've got electron withdrawing groups here, you're going to make this really positive and you're going to accelerate the step. If you've got electron donating groups, you're going to mediate that positive, you're going to make it less positive, you're going to slow it down. So this side does match this as being the rate determining step. Okay, but what's going on in step 2 over here? Okay, so in the rate determining step, we can see over here that at this side we've got electron donating groups who are on the electron donating side of the graph. Can you see that electron donating groups slow this reaction down? But electron donating groups over here, imagine an electron donating group pushing those electrons away. So electron donating group makes that go fast. So that's interesting. On the left-hand side of the graph, what is the rate limiting step? The rate limiting step is always the slow step. Electron donating groups on the left make this fast. It's not rate limiting. It doesn't define the rate law for this reaction. But over here, electron donating groups make this slow. And so that's why we're seeing this positive slope, because the slow step is being dominated, is being made slow by those electron donating groups. I hope you can see that electron donating groups make step 3 the slow step. If step 3 is the slow step, then we can see step 3 involves a movement of electrons towards the probe, and so we're going to have a positive slope. On the other hand, let's have a look at the other side. On the electron withdrawing side of the graph, if you have electron withdrawing groups, can you see that electron withdrawing groups make this step fast? So that's not going to define the reaction. The reaction is always defined by the rate limiting step, the slow step of the reaction. So electron withdrawing groups make sure that this is fast, and that's not a problem in the reaction. And so, well, what happens with electron withdrawing groups here? Imagine putting an electron withdrawing group here, how difficult it is to lose that water. So this now becomes a slow step. And we see that negative slope with electron withdrawing groups because this step 2 becomes the slow step. Okay, and of course, you can see that in the slow step, there's movement of electrons away from the probe. And because there's movement of electrons away from the probe, we see that negative slope. Okay, so there's this interplay between the fast and the slow steps. If you've got electron withdrawing groups, you make the one step so fast that the other one becomes rate limiting. Similarly, if you've got electron donating groups, you make the other one so fast that the first one becomes rate limiting. So there's that interplay between them. And so what is happening here, what really is happening here, is that we have a choice of rate determining step. There is only one mechanism available to us. Okay, and what happens is that, of course, let's move at the graph going from left to right. Start off with electron donating groups. Start off with electron donating groups, and you find that step 3 is rate limiting. So make them less donating, and this step 3 gets faster and faster and faster until you find a compound where it's no longer the rate limiting step. It's the other step that becomes rate limiting. So be careful. You see, if you make this reaction, can you see that with the paramethoxy, and as you get less electron donating, it's getting faster and faster and faster. But of course, when you reach this point, this reaction that's dominating is now too fast to define the reaction. It's too fast. As you move to the right, it's too fast. By the time you get past this point here, it's too fast to be rate limiting. And so it's the other step that becomes rate limiting, and it takes over in slowing this reaction down. Okay. So whenever you see a concave down plot like you see that, this means that there's definitely a choice in the rate determining step. And if there is a choice of rate determining step, which one controls? It's always the slowest step that is rate limiting. Okay, so this is different. The concave up was a choice of mechanism. There were two pathways available. In that case, it was the faster mechanism that took place. All the molecules were changing according to the fast mechanism. The slow mechanism had no chance to catch up to that fast mechanism. In this case, you've only got one mechanism. And as you have only one mechanism, what's going to cause this change is a change in the rate determining step. Okay. Right, I just want to answer as a final point to this mechanism is I want to know why on earth we use sigma plus. And that really is all about through conjugation electron donating. If you want to prove or show why we have to use sigma pluses, a really good group to choose is the methoxy group. It's really powerfully electron donating through conjugation. So what I've done is I've placed it in the para position on the probe, and I've had a look at the reaction intermediate on the left, and so we can see that when you've got a paramethoxy, can you see that the conjugation goes right the way through to the aromatic center? And so paramethoxy will accelerate, it really will accelerate that loss of OH2 plus far more than expected. So we can't use sigma values in that. We won't get a straight line. We've got to use a sigma Hammett substituent parameters that account for this through conjugation. And so we have to use sigma plus. And by simply drawing this mechanism here and showing the other resonance form, I'm showing exactly why we've had to use sigma plus. If I ever ask you to justify the use of sigma pluses or sigma minuses, please choose an appropriate substituent and show that the arrows go right the way through to the reaction center. Okay. So I've given you two interesting cases, two case studies that I would like you to know in detail. So when you look at questions you'll see I've asked questions about these two cases. One where there's a choice of mechanism, and of course, when there's a choice of mechanism, the faster mechanism prevails. And the second is where there is only one mechanism, but a choice of rate determining step. In these cases, it's the slowest step that prevails. Okay, and we've got one lecture left. This here really defines the end of the problem-solving part of the course. So you have all the information at this point to be able to plot Hammett plots and to make judgments based on those Hammett plots about the mechanisms that are proposed to you in questions. What I'm going to do tomorrow is I would like to explore variations on Hammett plots just to make you aware that the reactions are quite complicated and reactions are not just dominated by electron donating, electron withdrawing in relation to reaction center. Are there any questions? Okay, so the question is, do we answer a question like this by saying, using electron donating groups, step 3 is rate limiting, and electron withdrawing groups as step 2 is rate limiting. So let's go back here. So what we say is, yes, with electron donating groups, yes, step 3 is rate limiting, and electron withdrawing groups, step 2 is rate limiting. Yes, so you would answer it in that way, I agree, but you are missing just one small important piece of information, is that the link between the plot and step 2 and the plot and step 3. So what you need to do is you need to also in a question point out that step 2 will lead to a positive slope and step 2 will lead to a negative slope on the Hammett plot. Okay. Any other questions? Okay. If not, then we'll have a look at some interesting cases tomorrow, variations on the Hammett equation, and that tomorrow will be our last lecture.